Hello everyone, welcome to this week's ICT Strength Seminar. Today we are very happy to have Enrico from Cambridge, and he'll tell us about the ins and outs of the cosmological correlators. Over to you, Enrico.
Okay, thank you very much, Anurag, for the introduction, and it's a pleasure to present here. I hope one day I will be able to make it in person. Okay, so the title is this ins and outs of cosmological correlator. Is supposed to be a pun about understanding various ways to think about the natural observable of the very early universe, which are cosmological correlators. It's perhaps useless to say, but please do interrupt me during the seminar, especially in the early part. I'm slightly aware of the fact that the second half might be a little technical, and I would hate for people to get lost there. So especially in the first part, feel free to ask any number of questions, and please help me to make the seminar more interesting and more useful for everyone. So let's jump straight into it. I'm going to start with a very brief motivation, just one slide, a couple of ideas where we are going, where we would like to be in the medium term. And the main topic will be how the main observable for the very early universe in cosmology, which will be quantum field theory correlators in de Sitter spacetime. I'll review how these have been investigated in the past 20 years, and then I will point out that there is a different way to organize our calculations, still within perturbation theory, and I will discuss it. That the name of this different way will be the in-out approach, which is actually the very first way that we learn how to compute things in quantum field theory from undergraduate courses. And then I'll show you how this reorganization opens up the door for a range of applications. And I will discuss a few applications. They will have funny names like pole bagging, recursion relations, and cutting rules. And the last point will be a little bit more conceptual. I will propose, based on this formalism, a way to define the scattering process and actually scattering amplitude in de Sitter space. And I will show that it obeys a remarkable property that displays unitarity, the conservation of probability, non-perturbatively. And then I will discuss what the outlook is of these results. So please do stop me at any time. This is my one slide of why I'm spending my life doing this, why I think that this topic is interesting. And really the slogan is that primordial cosmology and cosmological observations are really a direct observational probe of quantum field theory and presumably quantum gravity, whatever lies beyond quantum field theory, in Kerr spacetime. Both quantum field theory in Kerr spacetime and quantum gravity are subjects of which we have very little to no data, and so it's very useful to have nature telling us which way to go. And the idea of this connection is pretty straightforward. It's actually remarkably straightforward to some extent. It's just a one equation. So if you take out anything, this is the equation you have to remember, is that if you measure anything on large scales, I'm calling it delta, but it could be whatever you want. It could be the distribution of blue planets, red galaxies, neutrinos, dark matter, anything you're able to measure. But on very large scales, you really make a map. You're going to go to Fourier space. Oh, I still have this type. Okay, so this is not there. You're going to work in Fourier space. So you're going to go to K-space, and you're going to make a map and take correlation. This is just an observational thing. We have done this with cosmic microwave background for photons. We have done this a lot for galaxies with galaxy surveys and for dark matter using lensing. And the promise of our cosmological model is that this thing that you can measure is actually linearly related to the quantum field theory correlators or quantum gravity, if there is a UV completion to field theory, in a space-time that is going to be presumably close to de Sitter space-time. And the linear factor is something we know. These deltas are some so-called transfer functions. And within a certain model of cosmology, so to percent precision, we know what these functions are. So really, when we measure stuff at large scales, we are really measuring this correlator directly. This zeta here is a particular field defined in a certain way. It's a scalar field, and you can think of it as being simply related to the diagonal of this part of the space-space metric. This is true in some gauge. Okay, so this is the zeta I'm talking about. It can be defined in various ways, but and so this will be, so the goal of this talk is to understand as much as possible this object, this quantum field theory correlators, because we can measure it. Notice that so far we have only detected the one where the 2-point function where n is 2 on the left-hand side and n is 2 on the right-hand side. However, we know that there is a lower bound on how big the 3-point function is. This is usually stated in terms of this FNL parameter. And this lower bound exists because gravity is a nonlinear theory. So you cannot have all n-point function being 0 except for the 2-point function. Really, there has to be some interactions. And so humankind will measure these correlators, perhaps not tomorrow, but one day. And so it's interesting to study them. The aspirations of this line of research are varied, and it depends where you come from. On the one hand, maybe the simplest thing you can say, well, we are measuring physics beyond the standard model. As far as we can tell, the thing we are seeing for the distribution of stuff in the universe cannot be generated or explained using either fields or constants, fundamental constant in the standard model of particle physics. So we do need something beyond. For example, the simplest thing, the scale of inflation, is not coming from combining the mass of the z particle with the speed of light and some other constant. Okay, it needs some additional scales within physics, so some additional fundamental constants. And additional degrees of freedom. Another goal is to probe gravity to scales where we have never probed it. These are going to be very high energy scales, and we would like to check whether our understanding of gravity remains true there or if there are modifications. Eventually, we know that some modification will have to appear parametrically below the Planck scale. We would also try to understand, try to probe our understanding of quantum field theory itself. Much of our formal understanding of quantum field theory is based on Minkowski space, because that's the relevant one for particle physics, and that's where we have developed this theory. But we know relatively little of what makes a quantum field theory consistent when space-time is curved, and especially if it has different asymptotics from Minkowski. And finally, we would also like to see, eventually, we think quantum field theory is wrong, and it cannot be really local interactions, otherwise the UV completion seems problematic. There will be some form of no locality, perhaps some string theory or some other quantum gravity, and if we are lucky, we will get some hints of that in the sky. So this is the object of study, quantum field theory, and we have strong reasons to believe that the very early universe might have been described, at least approximately, as a de Sitter space-time. So to describe this, people in the past few years have taken different routes, and many ideas have been proposed. So one, which is perhaps the oldest one, is, well, if you want to compute correlators, just compute correlators, study correlators, don't mention anything else. Okay, this will be the approach that I will take here. I will just talk about the actual observables, which are the correlators so far. Another line of investigation that has been very fruitful in the past perhaps 5 or 6 years has been thinking of a somewhat more primitive object compared to the correlators, which is the wave function. This is the field theoretic wave function. And once you have the wave function of the universe, well, the wave function that describes all the fields in the universe, well, you are allowed to compute from it any correlator you like. Notice this is not exactly the wave function that solves the Wheeler-DeWitt equation, but is rather the large volume expansion of that wave function, which is the field theory wave function, the one that satisfies the Schrödinger equation. And much has been known about this, its properties due to unitarity, causality, etc. Another approach is to really think a little bit more broadly about possible interactions that go beyond the unitary time evolution and thinking about open system evolution. I might mention 1 or 2 things about this, but I will not discuss in detail. So really, this talk will be about thinking of correlators. What can we say? What can we know? Okay, so the starting assumption is this semi-classical limit in which there is a large classical background and there are small quantum perturbations on top. The classical background is well approximated by the Sitter metric. which is represented here. Eta is conformal time, and the Penrose diagram is this square. The part of this full inextendable space-time that is relevant for cosmology is the upper triangle, the so-called Poincare patch, or sometimes the flat slicing of the theta. Each one of these constant conformal time hypersurfaces is spatially flat, doesn't have curvature, hence the name flat slicing. This green line represents past infinity, what you might call the Big Bang from a cosmological point of view, perhaps. And we imagine setting some initial condition on this hypersurface. For the scope of this seminar, I will always assume that this initial condition is the Bunch-Davies vacuum. And we could set this initial condition by saying the system is described by quantum mechanics by some vector in a Hilbert space. And this is the first the vector we start from. And the name, what the game is about is to say, what does the universe look like at the very end? So the future infinity is this horizontal line corresponding to time going to plus infinity or conformal time eta going to 0. And we would like to describe the state of the universe there or all possible correlators that can be measured.
Enrico, does it matter that you're in the Poincare patch as opposed to global? It shouldn't matter for this computation, right?
I think it shouldn't matter in the sense that I'm still capturing a full Cauchy slice up perhaps to a point. Right. I know that sometimes there is confusion when you put constraints as to whether you're taking flat slicing or closed slicing, because it might look like charge conservations and constraints might look differently. But as far as I can tell, I cannot see a problem with these calculations. So within this calculation, I don't see it.
I see. Yeah, in quantum field theory, it shouldn't matter. So I guess you could just as well work in the global slicing with the Hartle-Hawking state or the Euclidean value.
Yes, I think it should be equivalent.
Okay.
I have a question.
Yes, please.
So when you are saying that the Big Bang is eta equals minus infinity, r equals infinity, what do you exactly mean?
It was just a form of speech. It's just a hypersurface. Yeah, it doesn't really mean anything. There is a null hypersurface that corresponds to the eta going to minus infinity. So if you take these coordinates, they extend all the way here. Those coordinates do not cover this lower triangle. Yeah, that's what it means. But space-time is smooth. If you take a geodesic, you just extend it. In fact, every geodesic from any point in the bulk will hit this hypersurface in a finite proper time. So actually but since this is a hypersurface, I can set a Cauchy hypersurface. I can set my initial conditions there. And then the whole space-time in the future of that will be the domain of dependence of that hypersurface. So I can choose my initial condition on that hypersurface. So Big Bang is just maybe a name.
My question is the Big Bang should be at a point, right? I mean, how can it be? I mean, it should be at the origin. It should be at r equals 0.
Typically, the Big Bang is a moment in time rather than a point in space.
Yeah. It is a moment in time and space.
No, not
maybe we can postpone this discussion a bit. You know, this is in the this is some discussion of the Penrose diagram usually, and you know, maybe we can go on with this.
Yeah, very nice. Yeah, we'll get back to it. Okay, so this is the Penrose diagram. So we can either have the wave function here, or from it, what we actually want to measure and observe are the correlators. So what are these correlators? Well, there is state of the universe is some state. I'll use bracket notations. I denote the state of the universe evolved within the interacting theory as this capital omega. And within that state, I can ask what is the expectation value of any number of operators. And I'm going to be interested in the product of local operators. And mostly I will work in Fourier space. And although in full generality, you might ask about unequal time correlators, most of what is observed is the equal time product when eta goes to infinity, because none of us was there around inflation. So what we can only measure is the value that these quantities take in the future. So this is already partial information that we have. Of course, to understand the problem, we should be asking all kinds of questions about things we don't measure, but this is what we actually eventually need to feed to our colleagues. if we're assuming that we understand the full system and we're describing the full system, then we expect that time evolution will be governed by some unitary evolution operator. And so I can choose an initial state in the infinite past. In this case, as I mentioned, I would choose the Bunch-Davies state, but you can make other choices. And then there is some unitary time evolution operator, which is basically the exponential of the Hamiltonian that evolves it in the future. I need to evolve also in time the bra as well as the cat, and then I insert my operators. The typical calculation is performed in the interaction picture, where the state evolves with the interaction Hamiltonian, and all operators are the free fields. They evolve according to the free Hamiltonian. And crucially, in the calculation, there is a trick that we perform to connect the full state of the interacting theory to this to the vacuum state of Fock space, and this corresponds to an I epsilon projections of my contour of integration, which ensures that interactions are effectively turned off in the infinite past. So I have some notion of what state I start with. If it was interacting all the way, this would be problematic. This is similar to what we do for scattering amplitudes. We assume that the particles in the infinite past are sufficiently far away that interactions can be turned off. Once you define this, then this is some product of operators, and we have very powerful techniques, mostly Feynman rules or others, to compute this quantity. So schematically, what I'm computing is that I start with some state, which is a vector in the Hilbert space, unitary evolution until the asymptotic future. This just rotates this vector, but maintain the length in the sense it's unitary evolution. I do the same for the bra and the cat, from the infinite past to the future, infinite past to the future, and then I can ask any question I wish for this new state of the universe at time eta. For example, the correlator of fields.
Hi, Enrico. I have a question about the formalism in your previous slide. Yeah. So you said interactions. We are assuming that it's turned off at very early times, but in interacting QFT, we do this because we say that beams of particles become very far away, and so interactions are perhaps not important as asymptotic future and infinity, future and past. But here it looks like, because the scale factor is very small in early times, things are much closer together. Why is it reasonable to ignore interactions in very early times?
Well, it's a bit tricky to say they're closer together because things also shrink as you send them back in the past. And so you have to calculate the combined effect of the two. If we were talking about scattering, you can just imagine that you see particles, one coming from the right, one coming from the left. Clearly, in the past, they were far further away than they are now. So that scattering intuition still goes through. In this case, I think of it as a necessary assumption, because in general, in quantum field theory, we really don't understand unless there is some symmetry reason that fixes the state. So in Minkowski, we know what the state is because there is a unique state that we say is Minkowski invariant. But unless we make that statement, it's hard to know what the state of the interacting theory is. We are only able to build our Hilbert space on top of the Fock vacuum using a finite but arbitrary number of excitations. So I think this is what we are able to do. Maybe the other motivation is that we have an idea that the exponential expansion of the background will dilute anything that is not this Bunch-Davies state. And therefore, that is the state that corresponds to this Fock vacuum. So we have the intuition that the physical problem, if you let it go for a long enough amount of time, will drive the system towards this state. These are the two. Yes, please.
Yeah, but the first one is still not clear to me. You said the intuition of particles going asymptotically far away still goes through. Why do we think it goes through? Because scale factor is very small in our early periods, right? So why do we think it goes through?
The scale factor is small, but they're moving away from each other. So you have really to compute the product of the two. There is also a shrinking. If you put them in a wave packet, the wave packet is blue shifting in the past, so it's shrinking. So whether they overlap or not is a more complicated calculation that includes their physical distance as well as the shrinking of their wave packet.
I see.
So okay. Yeah, we could discuss exactly what the scattering problem is.
Right. Yeah, thanks.
Can I ask another question on these grounds? As you
Yes.
said, so we are at some finite time away from when inflation happened, so we can see some part of the early universe. As you said, if you allowed inflation to go on forever, like 100 or 200 e-folds, then eventually, of course, you expect that things will get driven exactly to the Bunch-Davies vacuum. But observationally, do we have any sense of how accurate this process was in our past? In the sense of how much we can see compared to how, I mean, inflation we believe went on for some 60 e-folds or something, and not for arbitrary number of e-folds. So do we have any sense of?
Oh yeah. So observationally, well, there is this number 60 that is often quoted, but I think it's more something that goes back to the 80s. Now
Okay.
I would say 50 rather than 60, just in the sense that the number of e-foldings, we always think of it as the number of e-foldings of inflation before heating, but you can also think of that as the number of e-folding of hot Big Bang expansion. The two have to match because we're measuring the same scales. And because we haven't seen tensor modes, we know that the scale of inflation cannot be that high, so the number of e-folding maybe is closer to 50. However, it can easily be as low as 20, and everything just goes through. You just take the scale of inflation to be enormously lower than 10 to the 10 GeV or the GUT scale. So that's still fully compatible. This is just the amount of inflation that we do observe, and then there can be an arbitrary amount of inflation before that, and we have no constraint whatsoever on that. So I would say the one we observed, the bound, when people actually ran it through the data, they found that number of e-folding is between like 55 and 20, but anything in between goes. And before could be infinite, as far as we can tell. The fact that the data fits so well, it means that you cannot have some phase of, let's say, radiation or matter domination, which is within 5 e-foldings before of what we observe, because the remnant of that would screw it up. Perhaps another comment on that is that it's only when you start with a universe that has accelerated expansion that you can choose a vacuum state at short scales, and then it gets populated. If you have decelerated expansion, you always get perturbation coming in from super horizon, and it's very hard to even say what is a reasonable state for those. That's another technical problem.
Okay.
So, yeah, thank you.
I'm sorry, can you repeat how there's an upper bound on the e-foldings? I understand the lower bound, but what about the
lower bound? The upper bound is that if it is too high, you need the scale of inflation to be particularly high. And if it is particularly high, then you produce tensor modes, and we haven't seen tensor modes. So let's put it like this. So during inflation, let's say Hubble is constant, and then inflation ends, reheating, and then you start diluting the energy density of the universe, like 1/8⁴, because it's mostly radiation.
Yeah.
If diluted for a very long time, and we know what it is today, it means that at reheating it was very high, corresponding to the energy of the inflaton being very high, corresponding to the Hubble value being very high, corresponding to tensor modes of unobserved, that they would be larger than what we observe. So this gives a bound around 55 or so, depending on the model. In other words, the non-observation of tensor modes is a direct bound on Hubble during inflation, which is also an upper bound on the energy density of reheating, and therefore on the number of e-foldings.
Okay.
I have also a paper in mind where they actually play with data to put this bound there, if you ask.
So what is your final state? Is it the state at the end of inflation, or?
Yes, correct. Yeah, it's the time of state at the end of it.
But these states you don't see. I mean, the states that you see are at the threshold of where the CMB scale, right?
Yes, yeah, but by what I said at the beginning, measurement of the CMB are linearly related. Remember, I said that this, my very first formula, they are linearly related through function we know, known as transfer function, to the state of the universe at the beginning of reheating. So because of the conservation of curvature perturbation and the knowledge we have of the transfer function, actually we believe that measuring correlation on CMB or galaxy is really telling us the endpoint function at reheating at the end of inflation.
And I mean, how these transfer functions in general would be very complicated, because I mean, the space in which they're calculated, I suppose, would be in a plasma phase, right?
Oh yeah, but they're a piece of cake. They're just I can draw them for you. Like the transfer function for matter looks like this: constant and then 1/k² log k. They're simple function. In practice, for high precision calculation, they're computed using Boltzmann codes. And for the CMB, they're just sines and cosines with some exponential at the end. So they're very simple because plasma have linear perturbations, which are just acoustic waves in the plasma. So they're actually relatively simple. You can compute them analytically if you're interested in 1% precision. Thanks for your comment. Very good. So we have this formalism, and we can compute stuff. And so this is what we've been doing for the past 20 years. So people said, okay, this is the formalism, this is I compute. Now I choose a model and then I predict, or I choose a class of models and I do the calculation. And this is what the typical calculation looks like, because the interaction Hamiltonian is either coming from the expanding this exponential or this exponential. We have to keep track where the interaction comes from, either from the right or from the left. So graphically, we can say that the one coming from the right are black, and the one coming from the left are white. And then we integrate them over all possible time, all possible space, up to some future. And then we contract those with the external fields, and we get the result for a correlator. So the simplest possible, let's say the 3-point function with 3 fields and just a single cubic interactions in the Hamiltonian, let's say phi dot cube, the calculation would have contribution from h to the left plus 1 from h to the right. Each one of the 2 contributions is slightly more complicated, but when you sum them up, in general, there is a simplification, and you get the final result. This is, I'm not going to go through the calculation, but it's a simple integral. There are 2 things that you have to pay attention to. One is that the time integral needs to be done because there is no time translation invariance. So the integral is actually not trivial. In Minkowski, it would just be a delta function of energy conservation, but now it's some possibly complicated integral. Typically, is an integral of a product of Hankel functions, which is hard to perform. And 2, you have to check that for every vertex, there are 2 terms, left or right. So if you get something more complicated, let's say a 4-point function, now the first vertex, left or right, the second vertex, left or right. So if you have V vertices, that there are 2 to the V time calculations, integrals that you have to perform for every given Feynman diagram. Okay, so you just draw one Feynman diagram with V vertices, and there are 2 to the V integrals associated with it, and you have to calculate all of them. This is much more annoying than for an amplitude, where one Feynman diagram is one integral. And each one of those integrals are complicated because they are nested time integrals. This integral in time has theta function with respect to this integral in time. And moreover, each one of the terms is different. So let's say that R stands for right. If this vertex is right, the propagators corresponding to these contractions are different, and they depend on what the vertex is. So I'm going to call the propagator attached to a right vertex G right. And so the one that connects to right vertices is time ordered. It comes from the right, where it's time ordering, so G right. But if it connects a right vertex with a left vertex, it's not time ordered, because the 2 Hamiltonians are not inside the same time ordering. So it's a different propagator. So each one of these terms has different propagators, and you have to keep track of all of them. And so you get expressions like this that are similar but have different propagators. And when you do the calculation, all of these terms combine. In this case, there are 4 terms, and they combine in the result. Each one of the terms has spurious singularities that cancel out when you sum them up. And the final result is, yes, please.
No, please, sorry, I just, in the interaction you're using is phi dot cube, you said previously?
Yes.
The interaction vertices. That's because you want a shift symmetry in phi, is that right?
Yes, there are 2 reasons. For inflation is because we think that the perturbation should be shift symmetric. And this one is fully shift symmetric, so each one of them has a derivative. Another reason is that if you have fewer, if the number of if the 2 times the number of time derivative, well, let me write it down, otherwise it's going to be confusing. 2 times n time derivative plus the number of spatial derivatives has to be bigger or equal to 4, and then there are no IR divergences. If this is not satisfied, then there are IR divergences. For example, phi cube, IR divergence. It means that this integral in eta will give infinity if I push eta to 0. So in this term, 2 times 2 is 4, so I'm safe. 2 times 3, so I'm very safe.
I see, but can't we regulate those divergences in some simple way? I mean, in ADS, for instance, phi cubed is not a problem, right? So we could get a boundary correlation function and use conformal invariance to just regulate these divergences. Or are you saying that, at least for the cosmological correlators, you're saying it doesn't work?
Yes, so let me mention this bound that I'm saying here, it's only for n equals 0. For generic masses, the bound will also depend on the mass, because any massive field has an additional amount of decay. So this is only for specific delta equals 3 or delta equals 0 in ADS.
I see. So if you added a mass, then there would be no problem.
Exactly. Depending on the mass, there might be various, for example, for a conformally coupled field, where mass square is 2h square, then you either need 3 or more.
I see.
4 or 5. But 3 is IR divergent, but 4 is okay.
I see.
So then the counting depends on the mass.
I see. Fine. Okay, thank you.
The other thing that I should mention is that in ADS, you are allowed by the causal structure to put boundary conditions so that perturbations have some normalizable or non-normalizable fall off at infinity. Well, here you don't, because the boundary is space-like. But here you don't put boundary conditions in the future. So in general, they have all possible.
No, I understand, but I was thinking of doing the calculation as follows. You use the ADS calculation to compute the wave function of the universe. Then you analytically continue it, and then just square the wave function and calculate. So if the wave function of the universe is nice from the ADS calculation, then maybe, the final calculation, when you square and sum, doesn't have a problem. But you're saying maybe it does. Because the wave function of the universe will not necessarily have these divergences This is just
I think that's correct.
Yeah.
Well, okay, so the phase of the wave function will be IR divergent even for a free field. For example, for the free graviton, we'll have this k squared over eta. So that's, but okay, maybe this is just in the phase.
Yeah, but you'll square it, so it won't matter.
Yes, that's true for a correlator.
So yes, I mean the wave function is you just compute ADS CFT correlators, right? You'll get some wave function, and that will give you the coefficients in the wave function. So the 3-point function of some marginal operator will give you the coefficients in the wave function.
So but usually when you match that, you are stripping out the z to some power delta to match the, and so that z could be a divergent expression. What you strip out to identify bulk correlators to boundary correlators, you remove some factor, and I think that factor will be can be divergent in this case.
I see. Okay. Please go on. So you're saying, but if you just do the in computation, you will find there's an IR divergence, even for
actually we can. Notice here. It's very simple, so we can just do this. This is the integral. And let's say this one is just 1 plus k eta e to the k eta, and I have 3 of them. So eta going to 0, the one wins. So the integral is the eta over eta to the 4th divergent.
Usually what we would say is that divergence is some contact term in position space. It's analytic in 2 of the momenta, so we don't care about it. I mean, these divergences also occur in ADS, but we say, they correspond to some contact terms, and so we don't care about them.
Very good, yes. So they would be contact in the wave function or in a putative CFT. However, to go from the wave function to the correlator, you multiply times power spectra, and therefore these are not really contact. So let's say that let's make an example. So an example, let's say that psi3 is the sum of k cube. This would be a typical one that is analytic because it doesn't depend on two of them. So it's analytic in two of them.
Yeah.
But then if I want to do psi3, this is 1 over k1 cube, k2 cube, k3 cube times psi3.
I see. So you're saying contact interactions in the wave function don't remain contact when you go to the correlator because you divide by this and that gives you some.
Exactly. So the actual correlator in position space is not contact. While the putative CFT correlator would look like contact, but it's not.
I see, that's interesting. I see. So that's a general problem for computing this. Okay, fine. Thank you. You have to be careful.
I mean, so the CFT, even if we had one, which we don't, it wouldn't know about these terms, and this term would be relevant. I mean, people look for them in the data. In fact, the most famous one I just wrote down is the one that everyone is looking for.
I see. Okay. Okay. Thank you. Thank you very much. Yeah.
Hi, I have a naive question. Like as you saw, the 3-point and 4-point function are always real of something. Is it a generic pattern? Like.
Oh yeah, that's an excellent question. So there is a generic rule for when they are real or not, and unitarity constraints whether they are real or not. And I think that, let me try to be precise. If they are IR finite, then they're always real because of unitarity. So there is a constraint known as the Cosmological theorem that says something like psi of, very schematically, psi plus star of minus k equal lower points. And for contact, this would be equal to 0. So if there is no IR divergence, and then I can remove this minus sign in the analytic continuation, then this says that all of these things are real. And if lower points are real, then higher points are real too. That's a consequence of unitarity. There is a nice work that exactly studies this by David Stefanizin and Shi Tong and collaborators, in which they actually, the whole paper is about when is the wave function real, and there are some specific rules, and it depends on the mass of the fields and the presence of IR singularities or not. But in general, there is a large class of cases. For example, for IR finite massless field, it's all real. I can send you the reference if you want.
Thank you.
Okay, so are these diagrams that you drew in the previous slide, are they loop diagrams, right?
These are tree level.
Tree level. I mean, what is the upper line? I mean, where do the terminals?
Oh yeah. Maybe I should have explained this this notation. So here time is running vertically. Below is minus infinity. Above is time equals 0. So this line that I'm drawing here, it just represents the point where I insert the correlators, but it's not the propagator. So that line is just a reference point. If you want, I could have drawn the diagram just like that. But additionally, people put the top line to show that they're all at the same time.
I see.
So
okay, fine.
Thanks. Yeah, thank you for. It's a good idea to explain the notation. It's slightly different from the way people draw Feynman diagrams, and in fact, that's a kind of the goal of this work is to show this. Well, since time is going quickly, let me just mention that.
Enrico, we are not that strict about time, so yeah.
Okay. Okay, sounds good. Okay, sounds good. I'll take it easy. Let me mention that in general, the whole point of the in-informalism developed by first Schwinger and then really Keldysh went to town with it was to describe open dissipative dynamics with fluctuations, an open quantum system, the coherence, pure to mixed state. That was the whole point. That was the formalism was about. And the most general formalism allows for interactions when written as a path integral between the time evolution and the anti-time evolution. The U and the dagger are allowed to interact in ways that have not been written down in this case. Here, what I was writing down was just the case of unitary evolution. But the most general case, if it is an open system and it can interact with an environment, evolution might be non-unitary. So even though we are calling it the Schwinger-Keldysh or in informalism, actually, we are just using it in a very restrictive framework when we do cosmology. So the more general framework will have additional terms, and the more general framework will allow for density matrices rather than pure states. This is just a mention. I think it's interesting to understand density matrix, especially in the presence of gravity that talks to everyone, and it talks to a bunch of fields that we never measure. And you might worry that when you trace them out, you should really describe the evolution of the system as a density matrix. But that is the subject of a different talk, very related to this, but a different one. So for the moment, I'm just saying, I know the full system, unitary evolution, because I'm not tracing anything out. But in practice, I might want to do better than this. Okay, so what are the difficulties? This is really what people have been doing. Like if you take any paper, this is what they do. This is the calculation that they do. And really, I mean, Maldacena wrote his famous paper basically using this formalism to lowest order. But then a few years later, Weinberg showed how this in-informalism can be extended to all orders in perturbation theory. Well, one difficulty is that, of course, you have to do 2V integrals for every single diagram. And for higher, more complicated diagram, this is complicated. The integrals are hard because the time integrals are nested. And it's hard to do these Hankel functions integrals. And perhaps even worse is that after you've done this complicated integral, you don't really know what properties were general and what properties are specific to the model you're studying. Like if I just give you the result of a correlator, how do you know that it came from a unitary local and causal theory? What properties of it remember that it came from a unitary theory, one that didn't have, let's say, complex coupling constants? And so the goal is to try to understand this object a little bit better, and eventually, because we are going to be able to understand their general properties, and in some cases, we could even define them through their general property. And I'll show you that the calculation can be rearranged in a way that addresses some of these shortcomings. So this is the main message. I'll actually show you why this is the case and how to rearrange it. But the main message is that the calculation we've been doing, I described so far, and everyone has been doing for 20 years, is this in. And I told you, you have to sum over 2 to the v terms. There are 2 to the v terms because every vertex can be alpha, can be left or right, and the other can be left or right. So you have to sum. And then for every time I decide the vertices, I have to write down all the propagators, which are different. And then I do the integral and I stop at some time eta 0, which is represented by this line. This line represents eta 0. The main message is that there is another way to do the same calculation in which all vertices are treated the same. They all are minus I, H. All propagators are Feynman propagator, the standard time ordering. There is no more G++, G+-, G minus+, and G minus minus. And the only difference is that now the integral over conformal time goes all the way to plus infinity, rather than stopping at it equals 0. The mathematical claim is that these two quantities give you the same result. You just sit down, compute it for all cases, same result. So I'm going to call this the in-out formalism because you see, this is exactly what you learn in quantum field theory. Feynman propagators everywhere, integrate, and that's the result. This equality is true as long as the left-hand side and the right-hand side are well-defined. And in particular, it's true in the absence of IR divergences. If there is a divergence, the left-hand side is infinite, the right-hand side is infinite, though I don't know what it means for them to be equal. But if I consider cases, as Surat just asked me, where I have enough derivatives, that there are no divergences, or I have massive fields, then this is the assumptions that we do. The other assumption, of course, we start from Bunch-Davis, unitary evolution. And then any interaction goes, any field of any mass and spin. This leads to a significant simplification of the calculation and to a bunch of applications that I will discuss. So
I have another question before you go ahead. I mean, when you're talking about infrared divergences, where do the divergences come from? Because these are just tree diagrams.
Eta equals 0. So when you do an integral from minus infinity to eta 0 and then send eta 0 to 0, there might be some divergences because there is an infinite amount of volume. So the square root of g in the metric, which appears next to the integral, gives you 1 over eta to the 4. And that represents the growth of volume as the sitter expands. And when eta goes to 0, there is an infinite amount of volume. So unless the interaction you're talking about turns off in the future, it will be active for an infinite amount of time, infinite volume, and it will give you a divergence. If the fields are massive, they decay, and so the interaction shuts off. Or if their interaction has derivative, the derivative goes to 0 because of the expansion, and then again, the interaction shuts off. So when I say IR divergences, this is what I'm referring to.
Okay.
Thank you. That's useful.
Enrico, one more question.
Yes, please.
In contrast to all the diagrams you drew so far, on this slide you have all the insertions at different times.
Oh, yes, yeah. I claim that this is still true when they're equal time, but is also true for all unequal times. So it's even more general as an equality.
Okay. Thanks.
Yeah, thanks, Nava, for pointing that out. Yes, so it's even more general. Yes, please.
Yeah. So when you first introduced this in method, so there was a time ordering and then there was an anti-time ordered path.
Yeah.
So is it okay to understand that the message that you're trying to give here is that the anti-time ordered is now being flipped?
Yeah, that's exactly how it is. Yeah, so let's look at it in this more graphical way, which I think is a good way to understand it. So let's do it as you say. So the in, if we think of it as a path integral, this is the path. It's called the closed time path. You prepare the bra from minus infinity. You prepare the cat from minus infinity, and then insert. In fact, in the full generality, the real Schwinger Keldysh, these are just the two indices of a density matrix. Right index and left index, and you're preparing the density matrix, and then you insert. But if it is a pure state, you can think of them as being just the bra and the cat. So this is the standard in. The proposal is that, and in this one, you have to double the number of fields because you have to remember if the fields are in the top branch or the bottom branch. We know that we can play all kinds of games by rotating these contours. For example, a famous one, which Suvrat has already mentioned, is if you rotate each one of them by 90 degrees, but in opposite directions, so the contour is straightened and vertical, that's the contour that corresponds to Euclidean ADS. And then everything is along a single path ordering, if you want. The contour that I'm proposing here tries to maintain Lorentzian time, so everything is as more of a Lorentzian time interpretation, and there is still time ordering. So I'm proposing to just rotate one of the two contours into an out contour. In Minkowski, this is a known trick that one can play. However, I claim that it also works in the sitter. The main obstacle in the sitter is that conformal time, I told you, runs from minus infinity to 0. And so for this proposal to make sense, you have to imagine extending the space-time with now two de Sitter patches. In one, eta goes from minus infinity to 0, and the other one goes from 0 to plus infinity. So this part of the contour prepares the bra, and this part of the contour prepares the cat. And as long as the bra and the cat are prepared to what they should be, the vacuum, well, the Bunch-Davies of the interacting theory, then the calculation is correct.
So was the assumption of unitarity crucial in this?
Yes, that is crucial. Otherwise, there are all kinds of branch cuts here, and I cannot go through them in generality unless I know what they are. In fact, if I was talking about the full open system Schwinger Keldysh, then this would not be allowed. And that's why people doing Schwinger Keldysh, they don't really play this trick of sending in to in out, because it's really non-unitary evolution that they want to model. Typically, they have a pure state that evolves into a mixed state because of interaction with the environment. And that cannot be changed into an in-out picture. That is fundamentally different. But because most people in cosmology consider only this unitary evolution case, for that, you get a choice.
I see. Thank you.
Yeah, thanks, Nilay. Very good. So, so the proposal is that this straight contour, and this straight contour, of course, everything is time ordered. And so there's just one propagator, time ordered along this time, which is why we only have a single Feynman propagator. Finally, the last message before I actually show you why this is true is that written that way, you see that these two copies of the Poincare patch. The lower one is an expanding Poincare patch, and the top one is a contracting Poincare patch. They display a very similar causal structure as Minkowski itself. And so this makes it natural to think of a scattering problem where you define an initial state down here, define a final state there, and try to compute their overlap through time evolution. The proposal, usually we prepare both the bra and the cat from -infinity. So this would be this green time evolution. But what I'm saying here is that you can also prepare the bra from the future and the cat from the past. This is what we would do when we do an amplitude-like calculation. So these in-out correlators are really the ones that appear in the LSZ reduction formula, the one that you amputate to compute an amplitude. And so it is natural to define an amplitude from this. Good, so let me show you why what I'm saying is true. The in correlators we already discussed. This is what I wrote before, so I just copied. I just wrote it again to notice that another annoying feature of this is that the I epsilon is the opposite in two, because one is the dagger of the other, is the Hermitian conjugate. And so you have to keep track of where that I epsilon comes from. And that, of course, yes, it projects the vacuum. Yeah, there are a few technical problems with this I epsilon having the wrong sign, but maybe I shouldn't mention them there. But people found it really annoying for a variety of reasons that I can discuss. I slightly, as Nava pointed out before, I slightly generalized my definition of the in correlator, and I allowed for the operators to be inserted at unequal time, and I insert them all inside the time ordering. So as long as they are time ordered. Of course, if they're equal time, this is just the formula I gave you before, but if they are unequal time, this is, I want to define them inside the time ordering. So it's slightly more general. Now I want to define a new object, which is this in-out correlator. Now I only evolve from -infinity to +infinity with, in some sense, the same I epsilon, or if you want, the I epsilon looks like this.
So Enrico, in that previous formula, I really wanted to start with the vacuum and just look at the Heisenberg operators at time t. So I would have started with some operator that had a t and a t bar for every operator O, and you're saying it reduces to this. I would have started with something which just had a u and a u bar for every operator O, and then that's how I would have got the Heisenberg.
Oh, yes. Yeah, exactly. Yes. If you go from the Heisenberg, you introduce them, they all cancel out, and the one acting on the vacuum.
I see.
You have to invoke this Gell-Mann law theorem that you can project with the I epsilon, and then when you do that game, it reduces to this from the Heisenberg.
Yeah, no, that's fine. Except that when they're unequal times, there would be some pieces in the middle, but you're saying you can time order it this way.
Yeah, because they're inside the time ordering, you can put them all in front or all to the left. That's correct, yes.
I see. So you don't get any e to the plus IHT inside the time ordering. That's the main thing.
That's correct, yes. There is always a minus, because all the one in between the, I forgot if it is UU dagger, something like that. But inside the time ordering, you can take all of these guys out, and they will only, because they are time ordering, they will always go with the right sign.
I see. Okay.
Yes, yeah, that's correct.
Sorry, I didn't understand. You're computing the time ordered product of these correlators. So the operators O that you inserted, you have time ordered them.
That's correct, yes.
Oh, that I didn't understand. I see. They're not just unequal time correlators with arbitrary ordering.
They are time ordered unequal time. That's correct. So
I see.
The time ordering survive when you go to the interaction picture.
Understand. Okay, now it makes sense. I was getting confused. I thought they were just unequal time. But you're really time ordered and unequal time. I see. Okay.
Yeah. For Heisenberg, it is time order, and then it becomes this.
Fine. Thank you. Yeah. Now it makes sense. Yeah. Thank you.
Very good. Okay. Yeah. So then there is the in-out, which this is the other object. Now I define that the time evolution goes from -infinity to +infinity. And it's all time ordered, and everything is inside. There is only one time ordering that goes. For these two to have a chance to be related to each other, I would like the expectation value of the operator 1 to be 1. For in, this is already true because this is if O is just 1, this is U dagger, and it's 1. So for in out, this is not 1, and so I have to divide by the time evolution from minus infinity to plus infinity, which is what we call the vacuum bubbles when we talk about amplitude. So if you divide by that factor, then expectation value of 1 is 1. That's an easy way to think about it, which is what I'm saying here. Okay, so the claim is that these two objects are the same. Mathematically, you compute them, they give the same result. So we can compute B in, B in out, and they give the same result.
So can you show once again the formula for B in out, please? The final formula you had. I see.
Sorry,
that's in it. Yes, I see. Oh, I see.
So it's always minus, and
yeah,
everything is time ordered.
I see. But in Hint, you had to introduce these two de Sitter fields. Is that right? So when you compute Hint, you do the integral from minus infinity to 0. That integral has one set of fields, and then from 0 to plus infinity, it has a second set of fields. Is that correct?
Well, no, not really. I will just keep one field, and they will go all the way to plus infinity. But you're right that maybe morally you're right. You're asking how does it map back? Why is it the same as before? And yeah, I'll show you. It's not exactly as simple as that.
I see.
Meaning that if you separate them that way, they don't match one to one. There's some terms that needs to be accounted for, but morally that's the strategy. I'll show you the simplest example how they match.
I see. Okay.
I want to argue in a second that if you still have to separate minus infinity to 0 and 0 to plus infinity, we wouldn't have achieved very much because we still have to split them. But I will argue that we don't have to. Like in Minkowski, in fact, we don't. Because it is true that when you work in the time domain, there is a theta function, but in fluid space, you just put a smart I epsilon, and that keeps track of ordering. So you never have to say which one came first. You just put the I epsilon, carry through the calculation, and the result ends at the correct time ordering by doing it once rather than twice.
Right. Here the thing you would worry about is what the propagator is from eta equal to, I don't know, 0.5 on the other side to time, to the other side. I mean, from one side to the other side. And you're saying that's just a standard propagator. You just compute it in some.
Well, it depends what it is. It has a different I epsilon from what the global de Sitter propagator would be. Mm-hmm. In particular, in some set of coordinates, the global propagator would be xa dot xb, and this is an embedding coordinate to some power delta.
Yeah.
I hope I get this right, plus I epsilon, while now it is xa dot xb to the delta plus I times sine of eta a times eta b times epsilon. So if you're looking at points in two separated things, the I epsilon flips sign. Well, if they're in the same patch, then it has the standard sign. And this is because the time ordering is really first expanding and then contracting, while in global time, the time ordering is with respect to global time. So it is not the same thing. So it's a different Wick rotation of the Euclidean correlator, which I think is the key.
I see. Okay, thank you.
Thanks. We are actually working this out to write down in ways that is more ADS-like with maybe embedding coordinates.
I have a naive question. Like, I mean, in de Sitter space, the metric is not flat, right? So when you're considering the Lagrangian for all these fields, the metric will enter. And presumably they will enter also in the Hamiltonian.
Yeah.
So how is that taken care of?
Oh, yeah, it's always there. Every time I do a calculation, I put the metric. So when I write integral in the eta, I do this. It just so happens that in rigid de Sitter, this is just 1 over h eta to the power 4. So instead of writing minus square root of minus g, I wrote what it is in rigid de Sitter. Okay.
I see. So Enrico, as you said, in Minkowski space, this would be kind of a obvious statement because you do the in-out contour, it goes up, and then you put some insertions and it goes back. But the contour below has no insertions because you can put all the insertions at the end of the top contour.
Correct.
Therefore, you could have straightened it out. And in de Sitter, I guess people didn't think of it because it looks like time ends at the future surface.
That's exactly why.
if you just imagine that it extends, it actually works out all correctly.
That's exactly, yeah, exactly. So I think it was just people didn't think about it because there is no time beyond zero. So what are you supposed to do? And this is the mathematical purpose. If I wanted to push this, I would say that it is not crazy to think that there is one space-time that generates the bra and one space-time that generates the cat. In the most general case, this is a density matrix, and bra and cat are not the same state. And so it is a path integral that generates them. This will be two path integrals in two space-times. So it's not really completely nuts to think that in the problem there might be two space-times. But of course, in a pure state, they are very related to each other by some simple...
Right. I see. Okay, thank you.
Yeah, it does resonate with some ideas about brackets and stuff. But yeah, that's correct. Exactly what you're saying.
Sorry, just to ask.
Yeah.
So, is it kind of if I think of from the wave function way of computing it, the fact that there has to be a mod psi square, if I think of that as a path integral way, does that kind of mimic this, continuing this eta beyond 0 to plus infinity? If I would like to kind of see, if it has to, as you were saying, if it is matches with the init calculator, it will also match with the correlator computed in the wave function way. So in the wave function way, as also Subrat was saying, after you get the mod psi, the wave function, mod square it, and then in that step, it differs from the ADS-CFT calculations where there are no sources and you don't do derivative.
Yeah, I think that's what you're saying, right? Because you have bra 0, ket 0, and so you're saying ket 0 you can prepare by doing a path integral on a fictional copy of De Sitter space, and bra 0 you just keep to be. And the mod psi square Nile is just the psi star is giving you the bra 0, right? And
that's what I had it.
The ket 0. So I think what I'm understanding is you can imagine the bra is generated by some doing a path integral on different copies. Yeah, the nice thing is that I guess the propagators work out nicely, which I guess that's
the main thing. The propagator is just one, and then it's very easy to do all kind of combinatoric games. Yes, Nilay, maybe I'll draw it this way, which is the way I think about it. But I think it relates to what you're saying as the wave function. You're right that there is psi, which is the bra, and psi star, which is the cat. And the question is, how do I prepare the cat from a path integral? And I propose that you can either prepare it here, and this is a psi star, or you could prepare it from here. As long as you put the right boundary condition, and you will land on the same wave function.
Right, I see. Thank you.
Notice that this is eta equals 0. So you have to make it evolve a little bit more and then back to get the wave function at the right time.
Right.
It's not the mirror of that. Okay, so the claim is that these two things are true. This is known for Minkowski, but it's less obvious in De Sitter because time ends. So let me just show you first a formal argument of why these are true, but perhaps many of you have already had the intuition of why it should be okay. And then I'll show you some calculation. So the formal argument basically relies on this observation that if you do time evolution from minus infinity to plus infinity of the ground state of the Fock vacuum, then this must be proportional to the Fock ground state itself up to a phase. The phase is so that the right and the left match when you take bra 0 of this. So this is true. You can check this simply by, you can project this on any n particle state. You could project it on something like this and check what it is. And you will see that it's always proportional to a delta function that doesn't have support on physical modes. You will have a delta function of sum of positive things that can never give you 0 unless they're all 0. So if you buy that, in some sense, it's a kind of stability of this ground state, then you can start with in-out. There is only one time ordering from minus infinity to plus infinity. For free or up to a phase, you insert this U dagger here because it's hitting the bra vacuum. So you can just put it in. And then this U dagger is a bunch of anti-time ordering from minus infinity to plus infinity. And part of that cancels the part of the time ordering that you have here. They cancel each other. So this cancels this. And what you're left is just in itself. Because now it's anti-time ordering. These two cancel time ordering. So this can be done really formally writing equation. The way I like to think about it is just by drawing it, because it's the same thing. You start with
I have a question.
Yes.
Yeah. So the first line that you showed, that the free vacuum goes to the free vacuum if you evolve from -infinity to +infinity. So this is like, I mean, if I had a space time which is like doesn't have any time dependence, and I turn on time dependence, and then I have another copy of that space on the other side, then this won't hold, right? This is only holding because you have a time dependence from -infinity to +infinity, which you finally will give you a delta function kind of a structure. And then only.
That's correct. Yeah, if you do it to finite time, it would not work. That I agree.
Because it's true, no, you have two asymptotically Minkowski regions and you have time dependence in between, then the in and out state are not the same. I mean,
that's
it's
correct.
modular phase.
That's correct. You're right. You could just excite things. You're right. It's because of the specific ways in which this time evolution is doing it. It wouldn't be true in general. That's correct. I agree. And in fact, it was somehow surprising to me because everyone said there is particle productions because of time dependence, of non-adiabaticity, and perturbations do experience some non-adiabatic time dependence of the vacuum when they get to be of the order of the Hubble radius. The Hubble expansion for them is a fast process. And nevertheless,
I think it seems like the second copy kind of undoes those effects, the contracting phase.
That's correct. And it undoes it in a precise way that it keeps all the phases right to really get you back to the state without losing information. That's correct.
Yeah.
Okay. Yeah, thanks, Farman, for that. Yeah, that's correct. That's the thing we were actually most confused about. We thought this is never going to work, but it does.
How do we know that there's no extra phase? What you just said about delta functions tells you that there's no support for particles in this state. But how are we certain about the phase as well?
No, there is a phase. Yeah, this is the phase. This is some phase.
Okay.
Yeah, so you're right. Yeah, there is a phase. There is some e to the I theta. This thing is some e to the I theta. Cannot depend on kinematics. It has no parameters, but there is a phase. So when you do it, basically this is the vacuum to vacuum bubble that I divided by. You see, this is the same phase. Would be e to what? It's e to the I theta, so e to the minus I theta cancels when I go from here to here. That's how we realized that we needed this vacuum bubble factor when we define the in-out correlator.
Thanks.
Yeah, thank you. That's correct. Which is a mess. It's a complicated object. If you don't divide by it, you don't really know what it is. You can depend on the coupling constant. Yeah. Okay, graphically, this is the same calculation I just showed you. Start with an in, which is this contour. Then the claim is up to a phase. You can add an infinite amount of thing to it because it just gives you a phase. And then you do it in such a way that it goes in the opposite direction. So this part of the contour and this cancel as long as you only insert operators here, possibly at unequal time. Then those contours cancel, and then you're left with a single contour. That could stretch all the way to plus infinity. This is the line by line, the calculation we just did. In terms of your question about the wave function, I guess that's what I was saying, that I have defined that this defines my bra, and this defines my cat. Okay, this is an explicit check, which is kind of Raju was asking about how does it actually work? How do they match terms in this and this one? So if you do in, you either get the interaction for the anti-time ordered, which is this one, or from the time order, which is this one. One has the minus I Hamiltonian, the other has a plus I Hamiltonian, so those are the two terms. In out, there is only one term. And you're right that it's the right idea to split the integral from minus infinity to plus infinity. It goes from minus infinity to 0, 0 to plus infinity. But they have, of course, the wrong sign, so they're not going to match this one above, because one is minus, the other is plus. So the one from minus infinity to 0 match, because the preparation of the bra is the same of the cat is the same in the two cases. What really differs is the other part. So if you take the difference between this and this, there are two terms that are not identical. In particular, they have the same minus sign, so they add up. And you get an integral from minus infinity to plus infinity. But here is the crucial assumption of that it's actually a good check that I did the right I epsilon. From minus infinity, you come in with a negative imaginary part because of this. Because of this sign, you come in from minus infinity with a negative imaginary part. And then you go off also with a negative imaginary part. And this is minus infinity I. And so you can close the contour and you can prove that these functions, for all mode functions of any mass, they're always analytic in the lower half complex plane of eta. And so this integral is 0. So the mapping, I mean, you could say it's trivial, it is 0, but they don't appear to be the same term. They appear to be something that adds up to it and gives you some integral, which by residue is 0. So it's slightly harder to actually match. And we did a calculation for higher order terms like this. And you have to keep track of all of this. And we have a more complicated argument, but it still works. But they don't match one by one. You have to add them up in a clever way to find analytic function that integrate to 0. In other words, you have to recreate this path here is not nothing. It does do some phase, but so you have to recreate it in a way that you see this is recreating that contour that does nothing.
Could you just re-emphasize what is the thing that doesn't match one by one? You mean that diagrams don't match with diagrams?
Yeah, exactly. So let's say in I have this term. So this term here and this term here are just identical. So I can just cancel them. One is in and one is in out. On the other hand, the one that I would call B in left, the one that came from a Hamiltonian here, is not the same as the part of the integral from minus infinity to 0. Oh, I'm sorry. I canceled the wrong one. Let me do it again. Okay. So minus infinity to 0 G Feynman cancels with minus infinity to 0 G Feynman. These two cancel each other. And this one and this, they do not look identical. One goes from 0 to infinity, one from minus infinity to 0, and their sign is different. So if I take the difference of in minus in out, these two actually add up, and they give me a whole integral from minus infinity to plus infinity. And we were very worried because typically that's something, and so they're not equal because the difference is not 0. But that integral is always an integral with the right I epsilon. You see, these are kind of mixed I epsilon. So it can be closed only in half a contour, in half a plane, and it always gives 0, which
I see.
To me says that we have gotten the I epsilon right.
Okay, thanks.
Yeah, thank you.
So there's something that's confusing me. This is a simple example where you have a single contact vertex that you're integrating, right? Will you also show an exchange diagram now, or in your examples? Or?
I have it in the paper and I can show it, but I don't have it in the slide. Otherwise, it would be a 2.5 hour time.
I see.
I'm happy to show you the example.
I see. But the thing I'm worried about is in the exchange diagram. I mean, the same question I asked earlier. There would be in the in formalism, there could be a vertex on the top contour and vertex on the contour below, and there would be some propagator that connects between them. Now, in the in-out formalism, will you use the same propagator or this different I epsilon propagator? You'll use something.
For in-out, so my propagator for in-out, maybe I should write it explicitly.
Yes, I'm worried about the case where there's an interaction vertex on the top contour and in, and one interaction vertex on the bottom lower contour. And you connect them with some line.
probably this might be related to the fact that, when you are computing the Green's function in the bulk or the bulk to bulk propagator, there is an ambiguity, which is the solution of the homogeneous part of that equation, which you can always add.
Yeah.
Probably a fixing of that is allowing this.
Yeah, I think in the Inian formalism, you'd use some Weitman function to connect those, right? To connect the top and the bottom.
That's correct, yes.
Which is the homogeneous one. And here, is the rule that even on the in-out, when you have 1 point on negative, 1 point on positive, you use a Weitman function?
No, time order, always.
Or use time ordered. Good, but then you'll get some difference, as you said. It doesn't match by itself.
That's correct. It doesn't match one by one. So they're all. So this propagator here, like all other propagators, every single one, they're all Feynman, and they're all really defined by the Feynman way, where time ordering is what this drawing makes clear. Everything which is below comes before everything that is up.
I see. And this fact that you can write the difference as some analytic function, this is expected to work also at loop level, right? Even at loop level, this is supposed to be true.
It is supposed to be true, and I have to be honest, we weren't able to check it, but we believe it's true. The general argument suggests it's true, but it would be great if someone checked it, and we might try it at some point.
I see. Okay, thank you. Okay, I understand. Yeah.
Yes. Good. Okay, so now the last part is applications. Actually, this is the main starting point. Once you have this formalism, then there are an infinite number of fun things that you can do. Practically, I think this gives an easier way to compute things. But I want to show you 3 ways in which calculations are simpler. And maybe I'll be slightly brief because it's a little bit more technical, but I think some of them for me are really surprising. Okay, so in Minkowski, why is this useful in Minkowski? Because in Minkowski, if we work in terms of time, then we have all of this theta function for the final propagators, and they're a pain. But we know that if we go to frequency, we just put the I epsilon and we just do one integral and we're done. We never think, oh, did it come before or after? Time and I epsilon does it for us. So this gives you a different way of computing a correlator, which for me is something like I'd never thought about, which is obvious in hindsight. So suppose that I want to compute like a simple correlator, something like this. Now, this in-out way of doing it is just the product of 3 Feynman. 1 Feynman here, 1 Feynman here, and they're all Feynman. We know that Feynman is very simple in momentum space. So let's start in Minkowski, just because everything is simple there. So I know that this Feynman's just 1 over p squared, let's say is massless, plus I epsilon, there's 3 of them. This would be the calculation in frequency and momentum. If I want to find equal time correlator, I just Fourier transform back from time to frequency, from frequency to time, which is just this Fourier transform and I integrate in frequency. But because the Feynman correlator has a delta function of frequency, this exponent, if I compute equal time, this exponential is just e to the 0, so it goes away. So I only have to do some integrals in frequency of just a bunch of Feynman terms. But this is just a contour calculation, so just a residue calculation. Just all of these integrals just pick up the residue from each one of these factors. And the residue is the correct one given by the I epsilon. The I epsilon tells you if you take the residue on the right or the residue on the left. And lo and behold, the result is just the usual one that we get from the in formalism when we add the left term with the right term and they combine and give you this. And here you basically never really did an integral. You just added up some residues. So you see that this iconic 1 over k total structure emerges, which is the one typical of the only pole that it can have. The normalization is right. Notice that the starting point didn't have this omega total, so it really gets built up by adding residues to each other. In that sense, we call it pole bagging. You're just getting poles, and then it builds up. And this is valid for, of course, any endpoint function, including exchange. It's also valid in the sitter. So let me emphasize that this simplification also applies to the sitter. In the sitter, as long as we restrict to massless or conformally coupled, then we have this nice dispersive representation for the Feynman propagator, which looks like flat space, and all the time ordering has gone into this I epsilon, which is the key. So now any calculation is just the product of n of them. Let's say now we compute a 5-point function of conformally coupled fields in de Sitter. There are 5 of them. And the only thing you're supposed to do is to go back to do the integral in frequency to go back to time. The main difference from before is that now the 5-point function doesn't have a delta function, but has a delta prime, because there is no energy conservation in the Sitter. But okay, you integrate that by part, and you have a bunch of poles and do all of these integrals using poles, and it comes out the right result, which is this 5-point function in the Sitter, which is not a different result from what it would be in Minkowski. Okay, so this I think is nice, and hopefully will be useful in the future. But this is the level to which we developed it. The other one is that there are recursion relations. Maybe I should be quick on that. In Minkowski, just in Minkowski, we can compute now correlator just by multiplying things. The main simplification is that now that when you draw a certain diagram, all propagators are the same. So you might try to do just one integral at a time and see what the result is. This is what was done by Harkani Hamed, Benincasa, and Postnikov, but they were only able to do it for the wave function because the correlators had all of these different propagators and then they couldn't keep track of it. And that's why, in some sense, a lot of people started working with the wave function 5 years ago. Well, partially perhaps because of the SCFT proposal, but partially because the wave function is only one propagator. And I think now that we understand this, for correlator is the same. You can play all the wave function tricks for correlators, and you get the recursion relations directly for correlators rather than going through the wave function. Maybe in the interest of time, I'll just show you the result of this. So the claim is that if you want to compute, let's say, a complicated correlator like this with an arbitrary number of external legs like here, you can just remove this vertex at the cost of multiplying, literally just multiplying times this factor, where x1 is the sum of energies ending on one vertex, and y is the energy into a propagator. This is true, you see, for any number of loops. So it's, and this is an algebraic relation, you just multiply. So this gives you a recursion relation for correlators that were not known rather than the wave function. And perhaps this is useful if one is interested in this polytope representation of correlators, but we have not pursued that. Finally, the main thing that I started doing this, why I started doing this was because I wanted to see what unitarity looks like. And we know how to deal with unitarity for amplitudes. These are the Katkowski cutting rules or the optical theorem. And they work for amplitudes because we only have products of Feynman propagators. But now the correlator is also products of Feynman propagators, so we can just open Veltman's book and to some extent do what he did. Actually, I find the way Veltman did is extremely confusing, but the modern way maybe to think about it is that you start from this identity. This says that if you take n fields and you sum over all possible ways to group them into one group and another group, and you time order one group and anti-time order the other group with a minus sign alternating, then the sum is always 0. This is the famous result that time order plus anti-time order is equal Whiteman plus Whiteman for the 2-point function, but it's valid to all orders. And from this, now the idea is that you put this inside an expectation value, and this gives you relation among correlation functions to all orders. And there are infinitely many of them. So I'll just show you. I don't think we have a nice combinatoric way to write them all to all orders. So I'll just show you a couple of examples. Let's say that you want to compute something like this, which has a bunch of legs and a bunch of loops, but a single vertex. Then you divide the legs into 2 groups. Now you have 3 operators, legs on the left, legs on the right, and interaction. So this is first, second, and third. And now you can use these identities we had in the page before to say that the sum of these 3 terms has to sum to 0 because of the identity with this funny time ordering. So these are all partially or out of time ordered correlators. And then you can transform these into actual correlators. But the one where the time ordering is funny, it can be written at the cost of introducing an analytic continuation in energy, which accounts for the fact that some of the fields are outside of time ordering. And so this gives you an identity between correlators and their analytic continuation in energy. To make this a little bit more streamlined, there is a graphical notation. When you separate operators to the left with operator to the right, this diagram represents this contribution here. And then our identities can be just written graphically by writing a cut on the left, a cut in the middle, and another cut on the other side. And the sum of these three terms has to be exactly 0. So this gives you a nice necessary relation that contact correlators have to satisfy to all loops. B of energy plus -1 to the n, B of minus energy equals 0. So you can check that in all the calculation I performed, this was true. This is true in Minkowski and the sitter, so it's very powerful. In fact, it can be used to show that certain low energy effective theories cannot be written in terms of unitary evolution. And we have the same for, now that you understand the gist, for exchange diagrams with any number of melonic loops. Cut on the outside, cut one leg, cut the other leg, cut in the middle. This is the sum of 4 terms. And this lists, when you rewrite each one of these diagrams in terms of an actual correlator, as the sum of correlators and their analytic continuation in energy. And this is an identity for the loop integrand. So you still have to do the loop integral. And these are useful because we didn't really know what these consequences of unitarities were for correlators in perturbation theory. The only result was this cosmological optical theorem, but that was for the wave function. And so what people have been doing in the past 3 years was do it for the wave function, constrain it, and then come back to correlators. And that led to some surprises. There were some no-go theorems about parity autocorrelators that have been phenomenologically important. But here you just work with correlators from the get-go. You never look back. Okay, finally, maybe in the last 2 minutes of this talk, let me talk about scattering. This is going to be pretty brief. So first, I just want to mention that because of the formalism, it's natural to define a scattering matrix. You start with, instead of the vacuum, with an excited state with n particles, time evolve for an infinite amount, and project on n prime number of particles, exactly identical. Time evolution is integral from -infinity to +infinity, but now we know we shouldn't be scared about this in the sitter. Just eta goes all the way. Okay, what are states? That is standard. It's the initial state should be the tensor product of unitary E-reps of the signal. They're classified by some Casimir operator and some, for example, momentum, spin, and angular momentum in one direction. You take tensor products of this, evolve, and project onto tensor products. It seems to be, so people have thought about scattering in the sitter for many years, and there are a few proposals which are very similar to this, mostly the Marolf and Morrison, but also more recently by Pimentel and Melville. And there are common criticism of why this should not work in the sitter. Some people worried about IR divergences, which might be a good worry, but here we assume from the get-go there are no IR divergences. People worry about particles might be unstable. However, in the infinite future, in the infinite past, with Ri epsilon prescription, all interactions turn off, so particles are actually stable. People worried about the blue shifting as you reach these null surfaces, but I think that that is just a coordinate artifact. Particles should be allowed to cross this eta equals infinity hypersurface because they do in global coordinates, so there is nothing wrong. And so we think this is, as far as we can tell, it seems to be a reasonable object. So what does it happen if you compute it? Let me show you the simplest result. So I define an amplitude to be the part of the scattering matrix that is not the identity. So it's really the connected part. And then for amplitudes, we remove usually the delta function of energy and momentum conservation. But now there is no energy conservation. So we only take out momentum. Everything else is inside A. And so we're going to compute A. The simplest case is that you scatter n conformally coupled fields into n prime conformally coupled fields. And the result is very simple. It's this one-line result. It's just the coupling constant. If the interaction is phi to the n plus m, I should have said. Right. And instead of a delta function, you get a number of derivative of the delta function. The number of derivatives is n plus n prime minus 4. Indeed, if n plus n prime is 4, then the interaction is just phi to the fourth. We know that's conformal.
Sorry, Enrico, I'm missing something. Could you please explain a little bit how this is defined? Sorry, I missed something. What is the precise definition in terms of correlators?
Oh, it's not defined in terms of correlator. Now I'm just doing amplitude Feynman rules. And so
I see. I see. But the definition is what? That you don't start with Bunch-Davies, but you start with some excitation of Bunch-Davies in the past, and you could.
That's correct. For example, you start with the tensor product of a bunch of this. Each one is a one particle state. And I can tell you as a preview that it will look much better in embedding coordinates, but for the moment, this is just momentum eigenstates.
I see.
There is a nice notion in which you write this in terms of conformal primaries, but basically it's a bunch of single excitations, A daggers.
I see. Okay. Okay. Thank you. Thank you.
And then, so you have a bunch of A with different momenta, e to the minus I h minus infinity plus infinity, and then A dagger. And this is your scattering. You expand and compute by contracting, and you can do the calculation. There is also an LSZ reduction formula for this that relates it to correlator. However, I mean, at this point, this is overkill because you just expand this exponential and do the calculation and you get the result. But there is an LSZ that relates it to correlator, but it's not written. I will not discuss it.
Sorry, when you say that there is no energy conservation, but even the derivative of the delta function only hits when on configuration with conserve energy. You just differentiate the function which it multiplies.
Yes.
It has no support outside this thing, so it's in some sense still conserves energy.
Yes, I think maybe the word is confusing. It is true. It has zero support, although it has a little bit of support in the sense that it knows about this first derivative. But you're right. It's not. Yeah. It could be really bad. It could be like any function of E total, and that's what correlators are, or the wave function, which is much of the difficulty there. No? This E total appears everywhere, and you have to keep track of it. Now you're right. It's actually not that bad. It's always for conformally coupled fields delta function. To be honest, I'm not sure what would happen for general massive fields with general Hankel function. I would expect that it could just not be a delta function at all, that it could have support outside. So that would be maybe a better answer to your question. Just take a general...
Is it because the mode functions only asymptotically are exponentials for those cases?
Yes, exactly. Yeah, that's why it turns out.
Yeah, okay.
To be honest, I'm not sure if it will always be a delta function or not. I'm confused about that. In this case, it's definitely a delta function. All cases that I computed was a derivative of a delta function.
Okay. Okay, thank you.
It'd be great to do another calculation. Okay, so it's just the derivative of a delta function. Easy. You can compute a more complicated case, and things get messy. Now you have sum over different functions and different number of derivatives of a delta function. You see the function has some vague 1 over s structure, which is the same as in Minkowski, but the numerators get complicated. And we can do this calculation explicitly. The reason why I think this is really interesting is because this object is the object for which I know how unitarity acts non-perturbatively. So the main claim of why this object is interesting is because I claim that this amplitude defined the way I have obeys the optical theorem non-perturbatively for assuming rigid the system, but for non-perturbative fields. And the optical theorem takes the standard form. Scattering initial to final minus scattering final to initial star is the sum of all intermediate states of scattering initial to intermediate and final to intermediate. The derivation is identical to the one in flat space because the structure of the integral is the same. This is a non-perturbative result, and this is what me personally, I was looking for this for a few years, and I was trying to obtain it for the wave function from the cosmological optical theorem, but I didn't manage. But for this amplitude, I think this is it. This tells us it's a consequence of unitarity, and if you take forward scattering, meaning I equals F, then clearly this object is positive. because this is the mod square of something. And so we have positivity of some object, and this is going to be the thing we will use to prove positivity bounds in the sitter, which so far have never been derived in the sitter.
So non-perturbatively, Enrico, what is the definition of this object? Or you just want to define it in terms of these Feynman rules? If you just, in the de Sitter quantum field theory, what is the definition of this AIF?
Yeah, I would say it's this formula here. Well, sorry, maybe let me, in this formula here. So I take some tensor product of states, of irreps. So I never mentioned anything, just irreducible representation. They are well-defined perturbative tensor products. Time evolve operator, project onto tensor products. I would say that's
I see. Sorry, but the plus infinity doesn't exist in the de Sitter original quantum field theory, right? You only have minus infinity to 0 in the de Sitter. That's what I was asking.
Oh, yes. Yes, yeah. One could imagine defining a bigger space-time where the two are glued. The problem is that it always takes an infinite amount of proper time to reach the future conformal boundary. So if you have a particle below, it will never make it at any time above. However, you can find a way to match boundary conditions such that you still glue these two space-time together and define a physical evolution. That would be one way of doing it. If we were talking about conformally coupled fields, this boundary, actually the conformal factor that diverges always is removed. This is related in some sense to the fact that in conformal field theory in Minkowski's, in Lorentzian Minkowski, they're not really defined in Minkowski, but they're somehow defined on this Minkowski repeated onto itself that becomes this cylinder. And there is some mathematical object that is defined on copies of it, but it reduces to within a single one. Probably the formal mathematical way to define it would be this, but you're right that I don't have a non-perturbative definition within a single de Sitter.
Okay, thanks,
Yeah, I have a question about positivity bounds. So it's like a conceptual objection. So you can, I mean, naively, you can imagine a scenario where you have unitary time evolution in one copy and let's say some open evolution in the other copy. I mean, some non-unitary evolution in the fake copy. So the S matrix won't satisfy in this unitarity bounds, but that doesn't mean that the original de Sitter space doesn't have unitarity. So it's not clear why it should put it should classify theories in de Sitter space which are like consistent with unitary UV completion, because you're adding something in. So yeah,
this time evolution operator here, U, when eta becomes positive, is not just an arbitrary quantity. It should be the same time evolution operator that I had before. You're not allowed to make the time evolution operator different for negative eta to positive eta. It should always be given by this, for example, perturbation theory.
No, I'm saying this object, the unitary, let's say this object doesn't satisfy, I mean, unitarity bounds.
Oh,
does that mean there is no unitarity in de Sitter? No, right? Because the second copy can have something.
Yeah, this assumes that we are doing yes. This assumes that we have a closed system and we are keeping track of everything. Yes, yeah. If there is open evolution, then this does not apply. I think you're right. Yes, yeah. This only applies to a closed system where we claim that we describe a full de Sitter. Otherwise, I think you're right. It will not. This condition will not be valid. Meaning, this is the condition of unitarity in the UV completion of the closed system, but the condition for the open system will be modified.
So the statement is, if I take this object, that means I have some field theory in de Sitter space, then I extend it like this in this particular fashion, and if this object satisfies, if this object satisfies unitarity bounds, then the EFT is, I mean, has a sensible UV completion. Is that?
Yes. Yes. Well, we haven't written the unitarity bounds because there is an additional ingredient, which is analyticity. That's the one we are working on. But
yeah,
at least for the moment, I have some positive discontinuity. And what we are working on is to find the right variable that pick up the discontinuity from a Cauchy integral theorem. And k-space variables are the wrong variables. The correct variables turns out to be a cross ratio of embedding space coordinates, but I will not discuss that here.
Okay, thank you.
Very good. Maybe just last, because I'm sure people have to go. So sorry for taking so long. But I was actually excited by this, because the first time I looked at this, I said, there is no way that the left-hand side and the right-hand side are the same, because the left-hand side is, sorry, yeah, let's start with, the right-hand side is simple. It was just this delta prime, okay? And there is some factor when you write the right-hand side. It's just that when you cut, so remember now we are checking it for this diagram. So on the right-hand side, I just have two endpoint function contact, which were very simple, just delta prime. But the left-hand side was this messy thing here, having delta double prime and delta primes with complicated numerators. Turns out that when you integrate by part this delta prime, these two rational functions combine into something, and when you take the imaginary part of that, using the correct I epsilon prescription, magically it becomes exactly this. So we could check that the optical theorem is indeed obeyed in this, but it's a highly non-trivial way that it does. So we believe it's correct, at least in perturbation theory, but the argument is general. And so we're excited to use it in the future for something more exciting like positivity bounds. Let me conclude. So there is this new toy to play with, which is the in-out representation of correlators, assuming unitary time evolution. We just discovered it, so probably there are many games and one can play with it. It definitely makes some calculations simpler. It would be nice to investigate what happens if there are IR divergences, whether there is a regulator that preserves this in equals in out. It would be nice to see what to do with these amplitudes using the optical theorem. And I'll stop there. So thank you very much for listening.
Yeah, let's thank Enrico for a wonderful talk. Yeah, do people have more questions?
I have a naive question. Like in dissipate, and there is some statement in terms of this spectral condition, spectral function positivity, to check this bulk unitarity. Like people say, like the spectral the density, this sigma in a 4-point function of a Cayley-Lemon representation, that should be positive for the bulk theory to be unitary. Are this optical theorem can be related to that statement? This or
yeah, so that's an excellent question. I'm discussing this. So there were two groups that worked on that. Di Pietro Comazzo, Gordenko, Pernedone, Salei, Vasili, Hogervorst, and they both derived this.
Yes, I was referring to those papers.
Yeah. My understanding at the moment is that, okay, but I haven't finished the paper on this, but I think that the optical theorem is the amputated version of that statement. So their statement is about the 4-point function. You expand it in conformal partial waves, and the coefficient of that expansion has some positivity property non-perturbatively. I think that if you take that 4-point function, you write it, you amputate it, which you apply to it an LSZ reduction, that becomes an amplitude. And then the positivity of that rho should be the same as the amplitude satisfying this optical theorem. So I think this should be the relation between the two results. The reason why I like the amplitude formulation of the problem is because you have 4 less propagators to worry about. Like if you want to check what they say and compute that 4-point function for an exchange diagram, right? Like the simplest thing that you could write down is this. This has 5 bulk propagators in the sitter. So it's not an easy object to work with, while the amplitude would only have 1 because you amputate all the external one using LSZ. So my hope is that what they are doing can be more practically useful to compute in various models and put bounds stated at the level of amplitudes. So I think they're related results.
I see. Thank you.
Thanks. Ricardo, maybe?
Yeah, thanks for the great talk. Just one question. So for the causality here, like, I mean, your representation is very nice. Now you have the CTRS matrix. So, I mean, usually like in a flat space-time, like you have a nice relation with causality, even macro causality, but also micro causality, like with the S matrix. Have you thought about whether you can now say something finally about causality in the sitter from this representation?
I haven't. The way I would do it would be the standard way, which is, well, I thought just a little bit about it. The standard way would be, okay, there are some fields, and then you introduce phi of x, phi of y commutator. And then you say that the phi of x and phi of y commutator vanishes when x and y are outside of each other's light cone. Then you amputate this to get an amplitude, and this gives you crossing relation, where sometimes the phi is acting on the right and sometimes is acting on the left, so it allows you to cross particles. Even in flat space, people are still learning how to do this. Like there was a nice paper last year by Misera, Hannes Dottir, Caron Huo, and others, and Giraud. It's not even clear how that crossing is fully understood beyond 4-point. For 4-point, we think we understand it all. Causality, this micro causality here is represented for the amplitude by crossing, the crossing symmetry. But for 5 and higher point amplitude, it wasn't really understood. And in fact, I think that the result of their paper...
I guess I was talking about the 4-point, like now in the sitter, your 4-point.
I tell you why I was interested in that is because what they show is that from 5-point onward, they show that actually there is no crossing between an amplitude and an amplitude. Like such notion does not exist. Like the crossing of an amplitude is not an amplitude, but it's an in-in correlator, which kind of forces you to think they are doing exactly the opposite of what they're doing. They start with an amplitude and they end up with in-in, which is the opposite of what I have. For crossing, I have hopes that this works, but I haven't done it. But I would try to do this thing for a 4-point and see if it can cross. Before I want to do crossing, I need to have the right variables, because usually this is useful when you do some kind of Fourier transform, and it is the Fourier transform that has analytic properties because of the vanishing of this commutator. I think as of now, it's not obvious what is the correct Fourier transform to do. I think that just doing the naive Fourier transform, I think, does not give a nice result.
Isn't that maybe, I mean, ADS, there are some, I mean, okay, most of the studies been done maybe for Icona and ADS or something like that. Like here, I don't know if there is a similar notion. But I guess there is some kind of high energy notion that maybe you can learn something like in an approximate way. Although I don't know what's the analog of that is, like because of the different value of the conformal dimensions that here are on different kind of series. But there should be some kind of analog of that, I guess.
Yeah, I think it's interesting. Wide open. There's been zero work on this. Like if you want to be the first one to do this, I think no one has really said anything on this, so it's interesting.
Okay, yeah. But thanks again for a great talk.
Thank you. Omkar?
Hi. So my question was basically pretty much what Surat was asking at the very beginning about if you did this in some other coordinate system like global or say something else, then the way you approach the Scribe plus, the topology of your slices is different, right?
Correct, yeah.
So then in a different coordinate system, wouldn't it differ significantly, this doubling of the spacetime? And I asked this because we wrote a similar thing last year about doing a similar thing for static patch coordinates, but we were trying to find world line functions, Schwinger Keldysh functions. So I thought like there's a double geometry that we also define, but you can extend it to very large R, the static patch R, but then the topology of that would be like a circle, a sphere. And so I'm not sure how that would be similar to what you are doing.
Well, let me understand. I mean, for static patch, what did you double? Like, where was the
so we just took two static patches and we like attached them at the horizon. But you can actually extend it to
something like this.
Yeah. Yes, basically. But we only, okay, we do it in a slightly different way where, okay, I can't really draw, but the thing is like, it's basically what your diagram is, but you cut it off at the horizon. That is where you pinch it off.
At the
future horizon, you pinch it off. If you take your diagram of your doubling, and you just pinch it off at the
so I think it's a little bit maybe a matter of what are the observable that you want to compute. So usually when people work in the static patch, they only compute things that this observer can measure. So it's slightly different.
Yeah, that's a different question. I agree, but I was wondering if because what would happen at the asymptotic itself, because the topologies are different, right? So say if you were to do what you were doing in the static patch coordinates instead of Poincare, so
yes. And what am I computing? Because the thing that I'm computing doesn't really make much sense in static patch, because I'm computing correlators of objects here.
Yeah.
So that's why I'm asking, what is the thing that you have in mind?
That would just be like R going to infinity, right? Like in the static patch coordinates. You do approach the scribe plus, but it's just that you approach in a different way, where you go to a really large sphere rather than going to like a flat slicing, going to a
But I think that in static patch, well, maybe it's my misunderstanding of static patch, but I would say you can easily compute the correlator of these black crosses, but you cannot compute the correlators of the green crosses, because I mean, you need other coordinates to do that. And in fact,
no, you can just extend the static patch by just doing some analytic continuation of the R coordinate to large R.
Well, I mean, for maybe a 2-point function, maybe you get away with it, but for a 3 or 4-point function, the static patch cannot know 4 points, because there is no de Sitter transformation that brings those 4 points within the causal diamond of a single observer. So I don't think that a calculation in the static patch, unless it's fixed by symmetries, like a 2-point function, okay, it's fully fixed by symmetries, whatever it is in the static patch, you extend it everywhere and it will work. But for a 3 or 4-point function, my naive understanding is that a static patch calculation cannot tell you everything about, let's say, a 4-point function on the global patch, for example. That's my understanding.
Okay. But then I would ask the similar question for, say, even global de Sitter. Like in global de Sitter, would it still work? Because again, the topology of the scribe plus is different, right? In the way you approach it.
Yes, I think in global de Sitter, well, I haven't thought about it. It's a good question, whether I can formulate the same. And my guess would be yes, but I haven't checked any of the details. That's a good question. I would expect it should be possible to define correlators, like you mean some in correlators in global de Sitter. I compute them and I rewrite them as in-out in 2 copies of global.
Yes.
I would imagine that it should be possible. But
okay.
That this should work. So thanks a lot, Poincare.
More questions? Okay, there are no more questions, then let's thank Enrico once again.
Thanks, Enrico. Thanks.
Well, thank you very much for all the nice questions and for the opportunity. Talk to you all soon.
Bye.
Bye, Suren.
Thank you, Enrico. Bye.
Yeah, bye, Tunir. Bye, Dick Tanoy. Bye, everyone.